This video is on equilibrium and the equilibrium constant. We'll be using this set of notes from chapter 15. Let me turn this light off. Okay. So, all right. So this is the introduction to equilibrium and something called the equilibrium constant. So the first discussion, of course, is the word equilibrium. And equilibrium just means a state of balance, okay? Most people know that they have an equilibrium in their body, and it exists within the ear. And sometimes when you're sick and your equilibrium is thrown off, you feel dizzy, and that's because you've lost that sense of balance, okay? So equilibrium means a state of balance. There's two types of equilibrium. One is static equilibrium, and that's occurring when we're discussing something that's at rest, okay? No movement. So the best example of that might be like a tug of war rope, okay, that's equally being pulled on by two teams of equal strength, so to speak. That rope, that middle of the rope, would not be moving because it's in a state of balance. Okay, so that's probably the best example I have for static equilibrium. I'm sure there are lots of others, but in chemistry, we're not concerned with static equilibrium. We're concerned with dynamic equilibrium, which means that there's movement involved. We'll say includes movement. Okay, and so one of my kind of famous examples I always talk about when I introduce equilibrium is, if you can imagine a shopping mall, a 2-floor shopping mall that has 100 people on the first floor and 100 people on the second floor. And for sake of, ease here, we'll say they're all wearing the same clothing. They're all wearing a, black hoodie or something. And at exactly the same time, 50 people from the first floor take the escalator to the second floor, and 50 people from the second floor take the escalator to the first floor. Okay, so if you were to take a snapshot before and after those escalator rides happened, it would look exactly the same, because even though there was movement, there was no net change, which is a big deal in the discussion of a dynamic equilibrium, and we're going to get into that in just a minute when we talk about what chemical equilibrium is. Okay, so static, not so prevalent in the chemistry discussion. Dynamic equilibrium, huge deal, is what we talk about in chemistry. So what is chemical equilibrium? It happens when we have, so let's see, it occurs when the forward and reverse reactions occur at equal rates. Okay, so this is why we learn equilibrium after kinetics, because equilibrium is a discussion of equivalent rate or speed reactions between the forward reaction and the reverse reaction. And so the most famous thing that comes out of equilibrium is the double-headed arrow. Okay, where A is your reactant and B is your product, for simplicity here. And so what we have now learned is that some reactions are reversible. And so we don't always have A just making B. In this case, we have A making B and then B turning around to make A. And we got a preview of that in the kinetics chapter, but this is the full-blown discussion of reversible reactions. And it's a huge deal in equilibrium because it is why equilibrium exists. So, in the discussion of chemical equilibrium, what we could say is that your reactants are making your products just as fast as your products are making your reactants. Okay, and thus that reversible, my markers are dying, I apologize. Thus that reversible nature, to reach over and get a eraser. The reversible nature of this reaction, okay, is that A is making B just as fast as B is making A, but overall there's no net change. So the tricky situation is, if you were to look at a reaction, you might not even know that it's at equilibrium, because you might say nothing's happening, the reaction's over, because to you, a viewer of the reaction, it looks like nothing's happening, when in reality, everything's happening. It's just you don't see it happening because there's no net change overall, and that's a huge deal in this discussion. Okay, so moving on and getting a little more specific into the concept of equilibrium. Let's see. So, let's see. We're going to start talking about this reaction. Okay, which notice has a double-headed arrow. Okay. So, so we have this reaction that is a gas reaction into O4, creating 2NO2. And so we can talk about this in two ways. We can talk about the forward reaction. We can talk about the reverse reaction. Okay. So the forward reaction, of course, would be read left to right, like we always read it. So it would be N2O4, creating 2NO2. And if this reaction's elementary, which we're going to say that it is, I could write a rate law. Remember from Stoich, which would be K times the concentration of N2O4. Okay, and I'm going to call this K of the forward. Now, if I reverse this reaction, it would be read right to left, okay, meaning I'm going to write it left, right, but I'm going to flip it to NO2 gas, going to make N2O4, and again, assuming this is elementary, I can write a rate law, K of the reverse reaction, concentration of NO2 squared, okay. Now, we've already made a huge deal, which is that at equilibrium, the rates of forward and reverse are equal. Gonna have to get rid of that marker. Okay, so that at equilibrium, the rates of the forward reaction and the reverse reaction are equal. So what I just wrote right here, this rate is equal to this rate, which means this rate law, so to speak, is equal to this rate law. Okay, and it's going to kind of help us derive this idea of equilibrium. So I have rate forward equals rate of reverse. This should remind you a little bit of determining the rate law of a mechanism when we, did this idea of a reversible reaction. So I just said the rate of the forward reaction was K forward times concentration of N2O4. The rate of the reverse reaction was K reverse times concentration of NO2 squared. These two things have to be equal to each other, okay, based on this idea of equilibrium. So what we can do is a little bit of algebraic rearrangement. Take this concentration over to this side, take this over to this side, do a little rearranging, and we end up with this. Which is going to give us a constant, okay? And so what's going to come out of here very quickly is something that's described, as the equilibrium constant, which is, I don't want to say it's similar to the rate constant, but the idea of it being a constant is the same, okay? And so we're going to see in a little bit, not quite yet, how we deal with this discussion of the equilibrium constant. And the first thing we're going to do is look at the equilibrium constant in graphical form. Okay, so at the very bottom of your page, it says the equilibrium constant. And we're going to talk about this reaction. This is a common reaction that's studied in equilibrium. It's the Haber process, as some of you are well familiar. Okay, and I'm going to talk about this reaction graphically in two graphs. Okay, so I'm going to give myself a graph here and label this forward And I'm going to give myself a graph here and label this reverse. Okay, then I'm going to pick 3 colors. I'm going to assign the 3 chemical species 3 colors. So we'll say that N2 is green, H2 is purple, and ammonia is pink. And I'm going to draw this graphically. I mean, this is going to be a graph, I guess I should tell you that, sorry, of concentration versus time. And this really leads us to the discussion of the equilibrium constant. I think it's important that we look at this graphically. All right, so if we think about this reaction from the forward direction, in the forward direction only, that would mean I start with N2 and H2 in a container. And after some time, I produce ammonia. Okay, so if you think about N2 and H2, they're your reactants. And so they must be present in the container in some concentration at time 0. Okay, it's got to be something. 1 molar, 6 molar, I mean, I don't know. But it has to be some concentration at time 0. So I'm just going to make this up. I'm going to say that N2 has a concentration of this. I don't know. And H2 has a concentration that's a little bit lower of this. Okay, I'm just making these numbers up. But knowing that they have to have a concentration of something, okay, for this reaction to happen. Now, as the reaction progresses, the only thing that the reactants can do in terms of their concentration is to decrease, okay? And we talked about that when we talked about rates, that the reactants would be disappearing because the products are appearing. So my N2 is going to disappear. It's going to decrease, okay? So it's going to start dropping. And at some point, it's going to level itself out. And it's going to stay consistent. Well, the H2 is going to do the same thing. And I don't know if it drops more, I don't know. I'm just making this up. But H2 has to drop. It's a reactant. So maybe it drops down to here. But then at the same point, it begins to level off. Now, NH3 is going to look slightly different because NH3 is a product. So think about this. At time 0, there is no product. So NH3 has an initial concentration of 0. And the only thing it can do over time is to appear. So NH3's concentration is going to increase. And I have no idea where, if it ends up higher than these, if it ends up in between. I'm just making this up. Let's say it increases up to some point right in here, and then it also levels off. We'll see at this point, we have hit equilibrium, okay? Because look at those concentrations. They are no longer changing, okay? And I have achieved a constant. Well, what's really cool about this is it doesn't matter if I approach this reaction from the reverse. The same thing will occur. So if I approach this reaction in the reverse direction, then NH3 is your reactant, and it will start at some concentration. And the only thing it's going to do over time is to decrease. And N2 and H2 are your reactants. I just misspoke. N2 and H2 would be your products, who have a concentration of 0 at time 0. And the only thing they can do is appear as time progresses. And you can see that the same constant concentrations are occurring, okay? And so the graphical representation of equilibrium, I think, is so important that you understand that no matter where I start in a reaction, eventually, in a reversible reaction, eventually equilibrium will occur, and those concentrations will not change. And that, in and of itself, is the nature of equilibrium. So we've alluded to this idea that there's a constant involved, okay? There's that equilibrium constant that occurred when those concentrations leveled out. And it can be achieved regardless of where and how much I start with. So if you flip, there's kind of some blank space at the top of your paper. So we're gonna make up a reaction. So we're going to suppose I have a reaction that's 4 things. Let's say it's all gases. Then I can write an equilibrium constant. Okay, and here's where life gets a little bit weird because we encountered a K for the second time, except this time it's a capital K. And this is going to be the equilibrium constant. And the first K we're going to learn about is a Kc. Okay, so it's a capital K with like a sub C. And that C stands for concentration. So this equilibrium constant deals with molarities, okay? And so the way we write an equilibrium constant is the products over the reactants. And so it would be the concentration of my product D. And this is where equilibrium constant, capital K, differs greatly from rate constant, lowercase k, because the powers on these concentrations are exactly the coefficients, okay? So this would be D raised to the D power times the concentration of E raised to the E power over A raised to the A over B raised to the B. Okay, so the important thing to remember is that equilibrium constants are products over reactants every single time. So that's the generic way to do this. So let's do the reaction we just looked at, which was the Haber process. So if this was my reaction, okay, I should now, at this point in time, be able to write a Kc expression for this. Products over reactants raised to their power. So my product in this case is my ammonia. You know, I'm reading it left to right. Okay, I'm reading it in the forward. So the concentration of NH3 raised to the second power over the concentration of N2 raised to the first power times the concentration of H2 raised to the third power. And that's the Kc expression for this reaction. And at this point, that's what you should be able to do. Okay, so so a couple, let's kind of take a couple notes in this little space. We'll say a few things about Kc. Let's see, it's a constant for a specific reaction at a specific temp. And if that doesn't remind you of lowercase k, we have an issue. So in that case, capital K and lowercase k are extremely similar in that regard. Okay, so what else? Kc only depends on the equilibrium concentrations, not on the initial, which that's going to be a big deal later on. That's not so much a big deal right now. But because this is an equilibrium expression, these concentrations are at equilibrium. Okay? And, let's see, the last thing is that Kc expressions only include gases or aqueous substances. So if you encounter a solid or a liquid, they're just left out of the expression. Solids and liquids are left out. Okay, they're just ignored. So following this, there's three little practice writing Kc expressions. So if you'd like to do that real fast, I'll put the answers up. And then there's only kind of one other discussion point left. Oops, oh my goodness, left in this chapter. Or left in this section, I'm sorry. So you might want to pause this so you can think about these Kc expressions. I'm just going to put them up here. So remember, it's always products over reactants. Don't get that backwards. In these practice, they're all gases and aqueous, so everything is included. So basically, you just have to remember that it's products over reactants, and their coefficients become their powers, and that's it. Okay, that's the first step to writing a Kc expression. So those are your answers for that. All right, last kind of idea is that we can actually write another type of equilibrium constant, and it's not a Kc. And your title says equilibrium constants in terms of pressure, which are going to be Kp's. Okay, so here's kind of the stipulation. When all reactants and products are gases, we can also write a Kp expression. Now I'm going to use the same reaction we just did, okay, because it kind of drives home a really good point. So in this case, okay, this is again the synthesis of ammonia. We know we can write a Kc. We just did that a minute ago in that last section. Okay, we wrote a Kc with our concentrations. But because in this case, all my reactants and my product are all gases, I can also write a different expression that's called a Kp, where the P stands for pressure. Okay, so it's the same idea. It follows all the same rules as Kc's, products over reactants raised to their exponents, but it's in terms of pressure. So you can't use brackets anymore. Remember, brackets mean molarity or concentration, so don't use brackets. In this case, we're going to do that it's the partial pressure of my product NH3, and that whole value is squared. Okay, the partial pressure of NH3 to the second power over the partial pressure of N2 times the partial pressure of H2, and that value is to the third power. If that bothers you, you're welcome to put these in parentheses. Just don't use brackets because that is mixing the two Kc and Kp ideas. So a Kc you can write for basically any reaction, but a Kp has to be all gases. And the value of Kc and Kp, will be slightly, well, I shouldn't say slightly, they'll be different. So the point comes up is there a formula to convert between the two? And there is. And so there's a formula that says Kp can be calculated if you know Kc and if you know a few other things. Where R is the gas constant. Okay, the 0.0821, where T is temp in Kelvin. And delta N is the change in moles of gas. And it is moles of product minus moles of reactant who are gases. So this seems complicated, but it's not at all. So meaning if you look at this reaction here, you would, to calculate delta N, you would look at how many moles of product are gas. Well, there's 2. And then how many moles of reactant are gas? There's 1, 2, 3, 4. So this delta N would be 2 minus 4. In this case, delta N would be a negative 2. So if you knew Kc for this reaction, and we always know R, and they'd have to tell you a temperature, you would take R times T, raise it to the negative 2 power, and multiply by Kc, and you would have a Kp value. So if you flip, there's a practice problem, and I'll do it with you. And this is a conversion of Kc to Kp. So let's see, number 1, it says, there you go, look, the synthesis of ammonia. I told you this equation is quite popular in equilibrium, and I didn't lie. So there's my, sorry, that marker's kind of hard to read, but my blue was dying. So there's my equation. It says Kc is equal to 9.60. Notice Kc is unitless. We're going to talk about that later, but you can kind of not sweat it because Kc and Kp are unitless, which makes it really nice. So they want to know Kp. So I know my formula. I just learned it. So Kp is going to equal to Kc. They told me what Kc was, 9.60 times the value of R times T. They had to tell me a temperature, and they did. It's 300. So 300 plus 273 is 573. So times 573 Kelvin. And I'm going to raise that value to the change in number of moles of gas. And again, that was the 2 minus the 4. So delta N in this case is -2. So I'm going to take this 0.0821 times 573, raise it to the -2 power on my calculator, and multiply it by 9.60. And I got something that looked like this. As my value of Kp. Let me check that for a second. Oh, something seems wrong. No, that's right. Okay. So, now my second problem says, here, let me erase this. Problem 2, they give me a new reaction. So SO2 gas, Cl2 gas. This time they give me Kp. And they ask me for Kc. So here's my equation. So I want to isolate Kc, and you divide by this expression. So Kc is equal to the value of Kp divided by R times T to the change in moles. So Kp, 34.5 over R, what was my T? 303 Kelvin. So 576. Oh, I'm sorry. Oh my gosh, that was Kelvin. They gave me Kelvin. Ooh, be careful. Raised to the, okay, delta N in this case. Let's see. Delta N, moles of product is 1 minus reactant is 2. So delta N's a -1. So I'm going to raise that whole denominator to the -1. And when you do that, I got 858 is my value of Kp. I know right now you're not real convinced on like what does the value of Kc and Kp tell me, and at this stage we don't really know, but that's coming very quickly. So one thing, one kind of takeaway point here, and then this will be the end of this video because now it's getting lengthy. I apologize. So if you think about if delta N were to be 0, okay, which would mean I would have equal reactant and product moles of gas, right? Think about it. Product moles 2 minus reactant moles 2. They would be equal. And I would get a delta N of 0. Well, if delta N is 0, right, then this whole R times T to the 0 power goes to 1. And then Kc times 1 is Kc. So if you have a reaction where delta N is 0, your Kp and your Kc value will be the same. They'll be equivalent. That's a very important point, and a nice takeaway for this section.